Good day, grade 9s. Welcome to our 8th and 9th lesson for physical science. We will be looking at the topic reactions of metals. This is your teacher, Marshall A.C. Candiado. Right, so let's get straight into it. So in the previous lesson, lesson 7, if you guys remember, we looked at metals, right? We introduced the topic of metals, and we tried to look at the reactivity of the metals. We looked at how the metals can then be used in processes known as alloying, if you recall, made as alloys. We looked at where the metals here in Namibia are mined, where you find them, and you gave us different locations: Rubicon, Tsumeb, Swakopmund. But with the uranium, you say it's just slightly out of Swakopmund. So we discussed this concept of metals, and now we want to look at the reactions of these metals now with different substances. So in this lesson, we will look at the reaction of metals with acids, as well as metal carbonates with acids, right? And then, because I have said this is lesson 8 and lesson 9, which means that we will take 2 periods or 2 lessons to cover all these concepts. So which means we will also then in the next lesson look at reactions of metals with oxygen, as well as reactions of metals with water. All right? So let us please take a few seconds to look at these objectives, state the general equation for the reaction of a metal and an acid, as well as the other objectives that are there. Just pause the video for a few seconds, maybe 15 or 30 seconds, just to grasp the objectives of these lessons. Right, so if we look here, it now says reactions of metals with acids. And we are told that metals react with acids to form salt and hydrogen. That is, the general equation is given there: metal plus acid to form metal salt plus hydrogen. Metal salt plus hydrogen. So before we proceed, I just had an image on the background here of sodium metal, right? This is sodium metal, and it's good for us just to remember what the sodium metal looks like, right? That's what sodium metal looks like. And it's extremely reactive. It's extremely reactive. If we looked in this container where they store it, where they keep it, if we were to have sodium metal, we would keep it under oil, so that it's not exposed to oxygen. Sodium, potassium, these are extremely reactive metals. So if they are just exposed to oxygen, worse off acids. Acids, they will just blow at the moment that they will just be dropped into a container with acid. So they're extremely reactive. And it's good just to remember when we're talking about the properties of metals, that they are shiny, right? They are shiny, as well as other properties that you guys know of metals, right? So now let us look at some word equations describing the reaction of a metal with an acid. So I did the first one for you. I think I also did the last one. Actually, I didn't. Good. So I did the first one for you so that you guys can have an idea of what the equation should look like. And all of them, the word equations are done. So you will see the first one, it reads potassium plus hydrochloric acid to produce the salt, the metal salt, potassium chloride plus hydrogen gas. Potassium chloride plus hydrogen gas. And then I gave you the symbol equation, the symbol for potassium K, and the little s that is there in brackets. That is the state of matter, to say when you find potassium, it naturally occurs in nature as a solid element. Hydrochloric acid, we find it as an aqueous substance. Then it produces potassium chloride, the salt, which is also solid, and hydrogen gas. So you find that the potassium chloride is solid, the hydrochloric acid is aqueous. The hydrogen gas that is produced, when you write it as H2 gas. H2 with the state of matter being G, meaning that it is gaseous. Okay? So what you guys will do now is you pause the video for even 3-4 minutes and you complete these equations, right? You write the symbol equations for sodium plus hydrochloric acid, calcium plus sulfuric acid, magnesium plus nitric acid, and you write the respective products for these three reactions. So I'll give you 3 or 4 minutes to do this. Okay guys, I hope you were able to write the products for these reactions, right? For sodium plus hydrochloric acid, I hope you were able to write those products. Then another thing that I want to show you is we want to look at how when we are using these acids, hydrochloric acid, sulfuric acid, nitric acid, we use what we call dilute acids. We use dilute acids. So what's going to happen here, you're going to be shown how you actually dilute an acid, how you take an acid and you pour it into a container that already has water. I think this is a very important aspect in science and in chemistry, that when we are diluting acids, we pour the acid into the water, not the other way around. So if you are given a strong acid like hydrochloric acid, first what you do is when you want to dilute it, you put the water in a beaker and then you pour acid into the water. You don't put acid into a beaker, then pour water into the acid. That will be very dangerous. That will be very dangerous for you. So I will just show you just now.
Experiments in this lesson, we will be using diluted hydrochloric acid. Let me show you how we dilute an acid. For this, we will need a beaker with some water. A small amount of hydrochloric acid needs to be poured slowly into a beaker of water. And then mix thoroughly. Always add acid to water and never water to acid. Remember that you have to take great care when working with acids.
Okay guys, so I hope you were able to see that small experiment that was being done there, not an experiment per se, but how you actually get to dilute acids. When you dilute acids, you have to add the acid to water and not the water to acid. It's the same thing that you do when you are cooking. When you are cooking, you add the oil to the water, not the water to the oil. If you were to put water into a pan, right, and then you heat it, and then you pour water onto it, you will find that it will just go. I hope you guys have cooked and you've been cooking whilst you are there at home during this entire big holiday that we've had. So you would have observed that when you want to cook and then you put your oil in the pan and then you pour water into the oil, then that's not going to be the best way of doing it. What you do is actually you pour the water first and then you pour the oil into the water. That's how you go about it. So now, I'm sure you wrote already your results, your products for this reaction. And we are saying you'll find that in each of these reactions that what is the similar product that is being produced. Of course, you have the metal salt that is being produced, but you also have hydrogen gas that is being produced. So here we have detailed the test for hydrogen to say how then do you test for the hydrogen. But to test for the hydrogen, you bring a flame near the mouth of the test tube, which contains the colorless gas. You are having a test tube. You would have a test tube which you have a gas which you do not know what it is, right? And then when you test for this gas, for you to know that it's hydrogen, right, it will burn with a popping sound, right? You put an already lit splint. Remember how we did this reaction? For you to test for hydrogen gas, you take a lighted splint, and then you put it to the mouth of a test tube, and then it burns with a popping sound. That tells you that hydrogen gas is present. Okay, let's move on to the next concept, where we have a reaction. Remember, in this lesson, I will try to cover everything all the way to the reaction of metals with oxygen, but then when we are discussing it in the lessons, we will take 2 lessons to do that. So before we move on to reactions of metals and carbonates, metal carbonates with acids, just look at the reaction of hydrogen, how you would test for hydrogen. Just go over the simple notes. If you can go back to your grade 8 notes, you will find that there was a reaction of how we tested for carbon dioxide, how we tested for oxygen, and this is now how we test for hydrogen. So just take a few minutes to go over that material. Okay, so we also have what are known as metal carbonates. Metal carbonates, as exemplified by what I wrote here, we have calcium carbonate. Okay, we have calcium carbonate, we have potassium carbonate, we have magnesium carbonate. A metal carbonate is basically you taking the metal that you know, like this. I mostly made use of group 1 and group 2 metals. But remember, you can also take from, from the transition elements, the transition metals, right? From the transition metals. You can also use transition metals, and you can say lead, or you can say iron reacting with acid, or copper reacting with acid. Let's see if I can find an image of that for you. Okay, so if we were doing like an experiment and we wanted to see the reaction of, look at these elements that are on the screen right now. This is lead Pb. I hope you are able to identify these elements from their symbols. If you look at your periodic table, look for what Pb is, what Fe is, what Zn is. This is lead, this is iron, zinc, copper, right? And here,
iron nail.
What is being done?
Can you see that a stream of bubbles is produced?
Okay, so let me just reduce this one. You will find that based on the reactivity series, you will find that here with the zinc appears to be more reactive. Anna, if you remember in the previous lesson when you said, why do we put zinc, is zinc not reactive? So why is it being placed on top of, why is it being used to cut iron? And we say it is being used as a sacrificial metal because zinc, as you will find on the reactivity series, zinc is actually more reactive than iron, right? But we said that zinc is used to cut the iron so that it then gets to rust instead of the iron that is below it, right? And we call that what? That is basically a sacrifice. It's called galvanized iron, where you put zinc on top of it and zinc becomes the sacrificial element. Okay, so these are metals reacting with acids. Okay, so now looking at metal carbonates, we are now taking that metal and you have now joined with the carbonate. Carbonate is CO3, right? Carbonate is when you have a metal reacting with carbon dioxide in the presence of a lot of oxygen, and then you produce a metal carbonate. Okay, so you can then have these metal carbonates also reacting with acids. And what do they produce? These are the products that you have. When you have a metal carbonate reacting with an acid, these are the products that you have. You have a salt, carbon dioxide, and water being produced. I hope you guys are watching and are really paying attention because this is important stuff. So this is the word equation. Why I decided to have you guys write the symbol equations, because I need you guys to grasp this material and understand it, because this is chemistry and we write our equations using symbols. So when you learn how to write balanced equations with the relevant state symbols, I left out a step symbol here. Calcium nitrate is going to be a solid. Calcium carbonate is a solid. Nitric acid is aqueous. Right? We just think of it as being a liquid, but it's actually aqueous. Okay? Aqueous. So you guys will again write in, and you fill in the missing symbol for these reactions. So you can just pause the video for 2 or 3 minutes, and then you fill in these equations. Thank you. Okay, welcome back, guys. So now we want to look at the reaction of metals and oxygen. So observe that by now, if we're now looking at reactions of metal and oxygen, it means we have actually now transitioned to lesson 9. We've actually transitioned to lesson 9, and this is what we'll be discussing, and this is now effectively lesson 9. So reactions of metals and oxygen. That is the general equation for the reaction of metal and oxygen to produce metal oxide. The notes, I'm sure you can read those, but mainly we are focusing on how the reactivity series of metals then actually gets to determine for us which metals are more reactive or are most reactive with oxygen and with water. I made use of the group 1, group 2 element, this one, group 1 element, and the transition metal to show us our reactions. So you will find that potassium reacts readily and easily with oxygen because it's extremely reactive, whereas elements or metals such as gold and silver do not react with oxygen. Even under the harshest of conditions, they already react with oxygen. That's why you are able to know that if you buy a gold ring or buy a gold chain, you won't find it having rust or corroding or having, if you bought these fake gold chains. I know people like gold chains and then they buy fake ones, and then you find them becoming green or making your skin green or even causing harm to your skin. That's because they are fake. That's because it's fake. If you have a gold chain or a gold watch, it is going green. Let me just put it out there. It's a fake watch. It's a fake watch. It's a fake chain. So don't come around showing us your bling and saying I got a gold chain and I got a gold watch. It looks like it's gold, but it's actually not gold because gold does not rust. Yes, gold does not rust, and same with silver. They do not rust. That's why they're able to stay for very, very long periods, and they're untainted. Okay, so if we look at the reactions, what I did also is that I have, let's watch this as well. Let's watch this. This is basically
sodium,
the same
but it
metal.
goes duller lithium for any color change, grey, shiny metal. It is also fairly hard, but can be a closer look at the elements we will be using today. The alkali metals react spontaneously with water and with air. They must be stored in a waterless, airless container. They are stored in paraffin. When using the metals for experiments, they must
observe all this. It must be stored in a what? In a waterless, airless container. Right? These containers, these 3 containers, are actually of potassium, sodium, maybe calcium as well. And they're saying they must be stored in paraffin. Right? They must be stored in paraffin. That is to prevent them from reacting. That is to prevent them from reacting with the outside air, or for them to react with water. It's critical that you understand this. That calcium, the moment it's exposed to air, it will react. Potassium, the moment it is exposed to air, it will react.
be handled with care. Always use tongs or tweezers to hold them. Under no circumstances must the metals be handled with bare hands. They can be cut using a scalpel or a sharp knife on a hard surface. In the first part of our experiment, be cut with a scalpel. Lithium is removed from its container. Do you notice that lithium is a dark grey, shiny metal? It is also fairly hard, but can be cut with a scalpel. Next up is the sodium. Can you see that sodium is a light grey, shiny metal? It is fairly soft and can be cut easily with a scalpel. Did you also see that it goes duller very quickly after being cut? Lastly, we will look at the potassium. It is a similar light grey, shiny color as sodium, but it goes dull almost immediately when you cut it, making it difficult to see the natural color. It is very soft and is cut with ease.
Okay, so those are the metals that we'll be talking about, the group 1 metals, lithium, potassium, sodium, and so that these metals, they are soft, right? Don't confuse it. Like if we talk about iron, iron is not soft, right? Iron is hard. Iron is hard and you can't cut iron using a knife, right? But these are different types of metals. So the properties of metals, there is a general array of properties for metals, but observe that there will be different properties depending on the group where these metals are coming from. Right, so let's see that we have magnesium plus oxygen to produce magnesium oxide. That is a simple equation. You guys will then fill in the one for lithium plus oxygen to produce lithium oxide, zinc plus oxygen to produce zinc oxide. Okay, so please pause the video for a few minutes and fill in and write these equations. Please try to write them properly, balance your equations, and also write the state symbols. Observe that magnesium is solid, oxygen is a gas. Yes, magnesium oxide is a solid. Observe how also that the equations are balanced. It's important that you balance your equations. So pause your video for just a few minutes and fill in those respective equations. Okay, let us now look at the reactions of these metals with oxygen, right? We remember like she was using in this experiment using sodium metal. That is how then the sodium reacts with oxygen, okay? If you heat sodium in air, I'm sure you saw the flame. Look at the flame that is being produced when you heat sodium in air, right? Nice. Right? Let's look at that again. That is basically the product that is produced. Okay, it's usually white powders when you have then. So what they were doing first, let's go back here a bit. So initially what's happening here is that you have the sodium, okay, it's being burnt in air. In the gas jar, you have pure oxygen. Right? You have pure oxygen in this gas jar. And now you have heated the sodium metal, and that's going just to allow it to even react even faster, which is why when they just submerge, that's a tongue, right, that she's holding with, and then when you just put it in there, the reaction is just spontaneous, okay? Okay, let's now also look at, finally, the reaction of metals with water. Right, so metals react with water to form what we call metal hydroxides and hydrogen gas. Metal hydroxide. A metal hydroxide is, let's look at this equation. Let's jump quickly to this reaction where we have sodium reacting with water to produce sodium hydroxide. So you observe that metals react vigorously when placed in water and produce heat or may burst into flames. Such is the rapidity of the reaction. That is how rapid the reaction is, that they react spontaneously, they produce heat. So the moment you drop sodium into a container with water, you will find that the temperature of the water will increase. Heat is produced, and when heat is produced, the temperature will definitely increase. And they may also burst into flames, that's how fast the reaction is. spontaneous reaction. So what we have here are also some equations. General equation is that when metal reacts with water, they form metal hydroxide and hydrogen gas. Then the first equation that I did for you guys, because I am so kind, is sodium plus water to produce sodium hydroxide, 2 moles of sodium hydroxide plus hydrogen gas. Observe the state symbols. Sodium is a solid, water is a liquid. Sodium hydroxide is aqueous. Okay, it's an aqueous. It's aqueous. It's almost like a watery solution. Then hydrogen gas. So you guys can fill in for potassium and for calcium. The reason why I did this one as well is because I wanted you to see how the equation or the formula for magnesium hydroxide looks like. Because Mg, the cation for magnesium, is 2, if you know how to balance and how to write chemical equations and how to write formulas, then you find out why magnesium hydroxide has a formula like this one. Okay? So please, again, you fill in the blanks. And these equations for, what is it called? Magnesium, metals plus water, right? Metals plus water, then metals plus oxygen. I will want you to submit, as well as the one for carbonate, I will want you to submit these equations as your homework, right? So when you have written all these equations for the carbonates, reactions of metal carbonates with acid, metals plus oxygen, metals plus water, those completed equations, those are the ones that you write as your exercise, and you submit them on Friday. You submit them on Friday the 29th. Yes, Friday the 29th by 5 p.m. you must have submitted this work. Okay, so if this is now the 9th lesson or the 8th lesson, that means it's tomorrow. It's tomorrow when you submit this work, Friday the 29th. So, okay guys, thank you very much for watching the entire video. This is Marshall A.C. Candiado saying thank you once again.